2, Web3.
Greetings, developers, hackathon participants, and metaverse architects. Welcome to another workshop of 1.2 Web3. Today, I'm here with Bernhard of Fluence Labs, and we're going to go over how to use Fluence with building your dApps and more tips and stuff to help you out with participating in this hackathon. Welcome to the stage, Bernhard. How are you doing today?
Doing very well. How is everybody doing here? Thanks for being here. Thanks for having us. We're super excited. Love the logo 1.2 Web3. This is great. I wish I had come up with it. It's super cool. And yeah, happy to be here. And happy to get you guys introduced to Fluence and help you with your dApps.
Perfect. Now, I understand you have some slides to share with us to get us going today. If you want to share your screen, I can put that right up for everybody.
I do. Are we good?
All right. And we are. Take it away,
Excellent.
sir.
All right. Thank you. All right, everybody. As already mentioned, I'm Bernhard from Fluence Labs. And today I want to show you a workshop. We'll go over a workshop on how to build decentralized peer-to-peer protocols and applications with Fluence and Aqua. Well, basically, I've spent the next hour or so unpacking this very headline, and I try to split the workshop into two parts. One is, what is Fluence? How does it work? What are your tools? And then the second part, actually going over some code. And so right off the bat, what is Fluence? Fluence is a decentralized peer-to-peer compute protocol, has some tooling and a network. It's all open, public, permissionless, and open source. And the network is not Fluence's network, but it's bootstrapping a peer-to-peer network anybody can join as long as the participating peer is capable to communicate according to the protocol. So that makes it public and permissionless. So you probably all seen this, gone through this, so I don't want to spend too much time, but one of the reasons we are all very interested in Web3 and in decentralization with peer-to-peer is that we are not particularly happy with deplatforming, with censorship, with loss of control of our data, loss of our identity. And in the latter two cases, the monetization accruing to third parties, we really don't want to accrue all this to, particularly if they keep leaking our data and identities. And in the former two cases, obviously, it's extremely restrictive and not particularly democratic. So from the Web3 ethos, then, what we want to do is we want to decentralize everything. And we want to decentralize using peer-to-peer networks. If you just decentralize without peer-to-peer, it's not particularly difficult to decentralize a few servers. That's easy. What's not that easy is how to decentralize in a permissionless manner, and a manner that scales basically to a very, not infinity, but to a very, very large scale. And that's where peer-to-peer networks come in, because the very structure and of peer-to-peer networks allow you to scale while still maintaining the notion of neighborhoods, which basically the scalability at the worst comes at the cost of traveling through different routes, exploring the network ad hoc. once you've done it once, you cache it, so it's really, really quick. And this is where decentralization of peer-to-peer becomes super, super critical in Web3. So on the financial side, to the right, when you see crypto tokens sending payments over blockchain, it's done, right? It's happening. Smart contracts, same thing. And of course, DeFi, big deal. However, there are more aspects to what sort of comprises the decentralizable internet stack, and other than just at the substrate level of peer-to-peer. And one of them is storage. So getting control of our data, you look at solutions like IPFS, Filecoin, Arweave, etc., which are peer-to-peer network-based data storage solutions, which are fundamental game changers in how we as individuals or larger entities can control our data. And with innovations like peer-to-peer based content addressability as put forward by Protocol Labs, you actually really, really help attain a lot of attributes of the Web3 ethos, if you will, including not just control of data, but censorship resistance and de-risking deplatforming. Same for identities. If you look at the progress been made over the last few years in terms of decentralized identities, verifiable credentials, eGov to a certain extent, and alternative identity representations drawn from different social media or different environments, there's a very strong drive of capability to become self-sovereign of identity in the digital space. And actually, ironically, Microsoft is one of the biggest users of DID and proposers of DID, using as an alternative login process based on Ion and SideTree, which Microsoft actually developed and pushed very, very hard in DID. Then on the networking side, you start looking at, special social networks, the Facebooks, very easy entry, very, very difficult to exit, right? They basically own your data. They own you. They own your identity. They own the data. And that's not particularly pleasant if you want to move on, or if you run afoul of some terms you didn't even know that existed, and no recourse to resolve this. So alternatives are developing, like Mastodon, for example, and there is a variety of Web3-based or peer-to-peer Web3-based social media platforms that are sort of trying to come in. It's probably the most difficult nut to crack in the Web3 space, in the sense that you almost have to onboard a new generation and just wait out that the network effect in the existing social network environments deteriorate to the point that people just take their loss, if you will, the loss of their data, the loss of their connections, their social connections, and just move on. And lastly, this is where Fluence come in. We want to talk about decentralized computing. And you probably come across various aspects of decentralized computing already. So there's smart contracts, they're on-chain, of course, and they're very deterministic. So it's not a complete compute environment. It's not an entirely arbitrary compute environment. Blockchains are introverts, so you can't just push out data. You can't have long-running or even short-running non-deterministic connections, because other nodes wouldn't be able to rerun the transactions and verify within the block time, and on it goes. So there's a big use case, obviously, for smart contracts, but it doesn't cover all of compute. Then you have decentralized hardware marketplaces. So LivePeer Golem, for example. LivePeer, where you have codecs for videos, right? You encode and decode video at demand. It's super, super cool, but it's a very specific vertical, very specific application. So you can't just write some general business logic and run it on LivePeer nodes, which, it's fine, because this is where Fluence comes in. So Fluence is an environment for and a solution for general purpose computations in a decentralized peer-to-peer manner. And the way, very high level, you have some business logic, you write it in code, you compile it to WebAssembly, you now deploy these WebAssembly modules as services to one or more peers in the peer-to-peer network that host those services now, and then you use a particular language called Aqua to compose these services into workflows, which you then can turn into, if you do it right, if you set it up right, into decentralized protocols and applications. So that's what Fluence does at a very high level, and now the rest of the time we're going to spend on that. If you have any questions, just pop up and let me know, and I'll be happy to answer. So Fluence, decentralized peer-to-peer compute. All right, on the right we have our little peer-to-peer network, and hang on, here we go. And let's just say the green peers are client peers, and they could be a browser, for example. It could be a Node app. It doesn't really matter. Let's just say those are browser client peers. Then those three node peers are full-fledged Fluence reference peers, if you will, that are part of the peer-to-peer network, that constitute the peer-to-peer network, and they can host WebAssembly services. Relay basically just means that that peer is publicly accessible. It could be in front of some peers that are not publicly accessible because of NAT constraints or whatever, whitelisting. But relays are publicly accessible, and they still can host WebAssembly services. And then you have other networks. You have, I don't know, you have peer-to-peer IPFS network, for example. You have typical client-server architectures running in the cloud, for example, for microservices or APIs. And you can access those alternative networks or other networks, if you will, through writing WebAssembly adapters. So you don't lose what you already have. You can wrap it, you can use it, and you can compose it, and you can reuse it in a decentralized peer-to-peer environment, being fully cognizant that in the case of IPFS, for example, you are connecting to another peer-to-peer network that really lives up to the Web3 standard in terms of decentralization, whereas some of the more centralized cloud solutions obviously would provide a choke point in your decentralized application. And okay, so how does it work? Let's just say we have some text. And our text is 1, 2, 3, tab 3, colon plus 1, okay? And we want to now check this text for emojis. So we have a service here, let's call it the emoji injector. And we want to spell check it. So let's call this service here a spell checker. So on the client now, we have this text. You typed in this text, 1, 2, tab 3, colon plus 1, and now you write this Aqua script, which is not shown, and that basically says, hey, take this text, find the peer and the service that checks for emojis and injects an emoji. Could be a PNG, could be a link, doesn't really matter. And when you're done with that, take this updated text or unchanged text and run it through a spell checker. Once you're done with that, write that clean text to IPFS, and then take the CID and give it to the other browser, for example. So if you're the other browser, you end up with a CID, which you can IPFS resolve, and then you get this emoji injected spell check text back. All right. So we basically put all this together, this script and the data, and we now literally from this client, we push it out to some relay. It could be like any node. The closer, the better. But where closeness is something we may have time to discuss, and it doesn't necessarily mean physical proximity. And on this relay now, it basically looks at this blob you get there. It looks at this script, this workflow. It says, hey, I need to find this service on some peer to do this emoji injector. So it ends up going here. Now we say, oh, look, we got this service. We got some text. And look, in the text, we have a colon plus 1. So that's a thumbs up, right? So let's inject that emoji, whichever we're going to do this. Is there anything else to do? Yes, we need to find a service that on some peer that spell checks the rest of the text. So, oh, look, we find this service. And now we do a spell check, and we have 1, 2, tab 3 now, and it suddenly turns into 1, 2, web 3. It's a very special, super good AI-assisted spell checker that knows that web 3 is important. Now we have that, and now checking happens again. Is the workflow fully done? No, we need to write it to IPFS. Now this service that does this checking or the writing to IPFS, it could be on this peer, it could be on any other peer or a peer not depicted in this picture. Doesn't really matter. And when it's done, again, checks that blob. Is there anything left to do? Yes, we have to send it to your browser, the CID to your browser. And that's how it happens. So what you basically, so we have a blob, and we call it a particle. We get into this a little bit. And now we need some service discovery and some content routing, right? That's really what we're trying to do. And once we have those services, we find the service, we invoke that service, which executes then on some WebAssembly runtime. That some WebAssembly runtime is called Marine. And it's a general purpose WebAssembly IT runtime environment. So the WebAssembly we are using is not BindGen, which you usually find in front end, but it's actually WebAssembly IT that compiles to WASI. And that's it. So how does it actually work? Every peer needs to have certain components. And one of the components is that Marine WebAssembly runtime. The other thing I kept saying, hey, and we're checking this script, right? This Aqua script, whether something's been done. This is happening with the Aqua VM. So, which itself is a WebAssembly module that runs on the Marine runtime. We'll get back to all these gory details. So these are the two major parts that make up a peer from a content, from a service perspective. That entails service discovery and or initiation of service discovery and the initiation of routing. And that kind of processing is initiated through the Aqua VM and Marine. Marine at the bottom is the execution layer for WebAssembly, and at the top it's the composition layer, basically where your workflow comes. And these green things, as I mentioned before, we call them particles, are those blobs I was talking about. So those blobs, they're really, really important because, as you may have deducted from what I was telling you when I illustrated the spell check emoji injector example, this is a data push model. This is very different from a client-server model. In a client-server model, you would have had the green browser go hit the emoji injector, come back, update data, go to the spell checker, come back to the client, do whatever needs to be done, go right to IPFS, go back to the client, and then finally contact the other browser, either through a proxy or directly, and deliver the CID. In our case, in the Fluence case, it's a data push model. It keeps going forward. While you can report back to the client, you don't have to. And so you're basically offloading your entire execution into an infrastructureless environment, if you will. And this is made possible through this blob, which we call the particle. You can think of it as smart packet. And that basically has three parts. It has the compiled Aqua script, it has your data, and it has some metadata. Metadata basically is just did we check, what have we done? And that has a lot of advantages. Aside from allowing you to have this push model for data, this data push model, it also allows for other things, including signing and on various ingress and egress, and basically giving you a capability to audit and ostensibly rerun your execution, your workflow, if you want to verify that it's correct. So it gives you both authentication and verifiability at the runtime level, which is very important because Fluence is an off-chain protocol. And that's where the scalability and the speed and the capabilities, those capabilities comes in compared to on-chain, but you still get verification and auditability of your workflows, which is very, very important, particularly in non-deterministic environments. So that's the particle, very briefly and explained. And well, actually, we can skip that. So let's just go quickly over some tooling before we get to the code. So we have a Rust SDK. Right now, you write your business logic in Rust for the most part. You compile to WebAssembly. And you do this with the Marine tooling and the Marine Rust SDK. And one of the very cool features of this SDK is the following. When you write business logic, as you know, you run your unit tests or integration tests on that code. Great. And in Rust, this can be done with what's called cargo test. And that's your testing environment. And what Fluence Marine does, it allows you to not only obviously that comes with Rust, run the unit tests on your code, but actually on your compiled WebAssembly modules. So what you do is you have your Rust code, you run your unit test, whatever you want to do or not on the Rust code, you compile it to WebAssembly, which is basically cross-compilation, and then you have WebAssembly modules. Now you can use the same unit testing framework that comes with Rust to write tests that actually use the WebAssembly modules instead of the compiler. And that is on the raw language. And that is super, super important for you to test before you distribute your WebAssembly modules to one or more peers. There's also REPL with it, so you can interact with modules locally, which is also very, very cool, because you want to get as much local testing done before you deploy to peers. However, we also have Fluence.js. Fluence.js has the Aqua VM and the Marine VM, just like the Rust client. So we have two types of peers. We have a Rust peer, which is a full-fledged, full libp2p, full Marine VM, Aqua VM peer. And then we have Fluence.js, which allows you to create client peers, but also full-fledged peers with one limitation. In the Marine VM can't process services that are comprised of more than one modules. And there are some libp2p limitations as well, where libp2p is the lower peer-to-peer substrate all of our nodes are built on, our entire peer-to-peer model is built on. And so in addition to that, what that means is if you run if you create a Fluence, your services in Fluence.js as a long-running peer, node app basically as a peer, you need to run the node yourself. So it doesn't scale anywhere near as you being able to deploy your services to a large number of peers operated by other people. However, it's available and you can actually do a lot with it. Aqua, as I mentioned, so that's Fluence's peer-to-peer programming language. So one of the things Aqua does, so let me step back. In traditional client-server environments, you interact with REST or JSON RPC with your resources, right? You do your post, you do your get, you do your fetch, and even on the blockchain, on most blockchains, when you interact with your data, with your compute, with your smart contracts, use JSON RPC. You actually do not use the peer-to-peer layer. You don't use peer-to-peer communications for that. Blockchains use, for the most part, use peer-to-peer communications for finding other nodes, other peers, and to exchange data to drive the sync process. But as a contract user or listener, whatever you want to build, you use JSON RPC, and that's a very different model. In Fluence, you do not use JSON RPC, or you do not REST to access the services. You use peer-to-peer based communications on top of libp2p. And what Aqua gives you, it totally abstracts over the lower level requirements of building peer-to-peer applications and protocols, and just gives you a very high level language. And we'll see this in a minute, which is super ergonomic. I mean, if you ever have built low-level peer-to-peer applications, you will rejoice. I can guarantee it. If you don't, I'm very happy for you that you haven't suffered as much as some of your peers. And no pun intended. And that's a high-level language. It also comes with a compiler. So it takes that high-level language and compiles it into an intermediate representation. We call it AIR, Aqua Intermediate Representation. You can think of it as bytecode, but actually the output is more Lisp-like output, which then gets processed on the Aqua VM. Recall, every peer and client peer, including browsers, run the Aqua VM and can do all these things in terms of managing particle execution and initiating discovery and all this good stuff you need. And on top of it, it comes with a command line interface that is a very quick one-shot way of deploying services or running services. With Aqua also comes some libraries. So there's Aqualib, which is sort of a standard library, which gives you a whole bunch of functionality, just like a standard library would. And there are various integrations. So we have Aqua IPFS, which is an integration into IPFS. So you can use Aqua to seamlessly interact with IPFS without you having to write any additional code with respect to the interaction, which is super cool because you basically have one programming language to to work across two different peer-to-peer protocols. It's actually really cool if you think about it. We have Aqua registry, and there's other libraries to come, which basically really helps you with service discovery and publication of services, advertising, basically. And there are more in the works and coming. All right, so code demo and review. Are there any questions so far? I'm totally blind. I'm just looking at my screen.
I'm not seeing any questions in the chat.
All right.
Just
All right.
yet.
Okay. Thank you. All right. Let's just go into the problem statement. What we want to do is we want to decentralize the blockchain gateway. Blockchain gateways are super helpful, right? Infura, Alchemy, Link, Morales, super helpful. I mean, running those nodes yourself is very expensive. A lot of DevOps required, and particularly once you bring archive nodes in, it's just super expensive, and it may just not be worth your while doing it, particularly given the DevOps requirements. However, at the same time, those solutions bring a centralized component into your dApp. So how do you deal with that? And that's one way where Fluence can help you by basically building oracles or quorums over multiple gateway providers. And what you end up doing, it's basically called verification by replication. Like you replicate your calls, your requests across different instantiations of a service, and then you build a quorum out of this. So I used, for this particular example, I used Infura, Alchemy, and Link because I just had it. And one of the things they have all in common, which makes it easy for me to build the example, is they all give you direct access to JSON RPC for EVMs. So we have these three, I mean, there could be more gateways, and we want to build a quorum around them. So what we do now is we need to build an adapter that basically gives us requests to each one of those gateways. That adapter, this is our service, is going to be on some Fluence peer. But Fluence is a public permissionless environment and network, and you may not trust that peer. So there are different ways of resolving it. But without crutches or anything, you basically do the same thing what you did with the gateways. You basically triplicate, in this case, your requests, right? So you have an adapter for each one of those gateways, or one adapter that does for all three. And then on each one of those nodes, you would call each of the gateways. So you have a total of 9 requests in this particular case. You join all those responses, and now you do some calculations, quorum calculations, mode, frequencies, whatever. We'll get to this in a minute. And we have a service for that, and we deploy it to one node. Now, the assumption here is that we trust that node. Otherwise, you would do the same thing again, right? You would run that quorum on multiple peers and then bring it together and get to your quote-unquote point estimate. And I'm saying point estimate in this particular case because all we're going to do is query for the block number of Ethereum main chain. That's all we're going to do. Of course, you could do any JSON RPC call. It just doesn't matter. So getting a block number is interesting because you can use it usually as input for something else. You can feed smart contracts with it. You can do a lot of things with it. So it's actually a very simple latest block. It's a very simple procedure. The other thing that gets interesting is how you structure your code, because WebAssembly has 2 constraints. One constraint is it doesn't have sockets, and the second constraint is that it's single-threaded. So Fluence gives you tools to resolve both issues. The parallelization aspect can be done with Aqua, and the socket or workaround can be done with Marine. The point here is that, as you know, block times are tick, 13 seconds, roughly 13 seconds, at least before the merge. And if you just hit right at the block time due to latencies in your request, you actually might end up with 2 different blocks. And, they're actually both correct at the time of the call. However, you always want the latest. So one of the assumptions would be, the most recent wins. So there's a whole bunch of things you can do, and they're not particularly difficult to do. But one of the easiest things to avoid those kind of edge cases is to process as quickly and in parallel as possible. And this is where Aqua comes in. So what are our implementation requirements? What do we actually have to do to make this happen, to get this diagram implemented? We have to write WebAssembly services. And one of the WebAssembly services we have to write is this, I call it the Query Gateway Provider service. So that basically, hey, it takes whatever you want to query, in this particular get the block, latest block, and then makes an HTTP call to whatever URI in this particular case you give, which could be any one of the 3 providers, it could be 5 providers, whatever you set it up, doesn't matter, and then gets you back a block number. And then we have quorum calculation. So it's basically a statistical processing service that basically takes a bunch of frequencies and some thresholds, like a quorum threshold, and then determines whether or not the resulting number is a quorum. So for example, if you have, I don't know, if you get a block number which is 6 out of 9, we had 9, are the same, and your quorum threshold is 2/3, then it would be true. That block number, we would accept that as a point estimate for the block height. If our quorum threshold would be 90%, then it's like, no, we would reject it. So there are 2 parts of it. One is the pre-threshold value, and then whether or not we accept the value as a result of applying the threshold. That's basically it. And so those are our 2 core services we need. And then we need to write our Aqua code, and we basically compose those 2 services into the workflow we want. So basically, we compose these services into the sequence of, hey, on each one of those peers, do these 3 calls, do all this in parallel, join the results, now apply the quorum calculations, now apply the threshold, and give me a result back. Very simple, right? So, but we still have to do it. And so what we need to do is we need to write those WebAssembly modules. We need to configure and deploy those services. And right here, real quick, what's the difference between the service and the module? In WASI, you can't import directly from one module to the other. They're called shared nothing modules. You can only link them at runtime. It's part of the security model and part of the WebAssembly determinism requirements. And so you basically write modules, and then you write runtime linking instructions. Part of it is a module, part of it is through a JSON file, and then you basically create this service instantiation of this configured modules on peers. So the minimum number of modules for a service is 1, and the maximum number, I don't know, probably, infinity minus 1 or something like that. But it could be, and usually are multiple modules that make up a service. So service is fundamentally a virtual construct based on the configuration of WebAssembly modules, which introduces a lot of interesting attributes, including reusability, shareability, deduplication, and all this good stuff to make things more efficient and easier on developers. And then finally, we have to implement the composition and the control script and run it. Okay, so let me switch real quick. Okay, why is this all coming up? Something went wrong.
Just giving you a second to get switched over here.
I don't know, something wants to update. I don't know why. I don't want you to update. Code. Okay, so we're a little over half hour in. All right. Got to hustle here. All right, if you look to the left on our project layout, so we got a directory. Some of the files you just ignore. Anything with .back.
Bernhard, any way to zoom in a little bit on the section you're talking about? It's just the print's a little bit small for us here.
All right, let me see. How's that?
Oh, beautiful.
Okay, so if you look at our project setup here, so we got the folder for Aqua. This is where our Aqua scripts go. We have a folder for artifacts. This is where we put our compiled WebAssembly modules. We have a folder for config. This is where we have various config files, including the deployment config we talked about before, in order to provide link instructions for the modules to quote unquote become a service. There's some old stuff which doesn't matter. There's some parameters we'll use to do some running examples. We have some scripts, which is actually just a build script. This is how we compile all our WebAssembly modules in one fell swoop. I'll show you this in a minute. And then we have our WebAssembly module code. The multi-provider query we talked about before. And this is what it sort of looks like. And there's a bunch of structures or interfaces depending on how you look at it. But what's the most important part is, maybe let me make it a little smaller. Is this still good enough? Can you still see that?
Still looks good, I think.
Okay. So our core function here is called get block number. We'll give it some provider information, but provider information is an interface or data structure basically comprised of the URL for the provider and the name of the provider. So it could be, I don't know, Infura and whatever URL. It could be Morales, whatever URL. And the method we're using in this particular case is the ETH block number, which is documented in the JSON RPC specs. And now what we're doing is we format all this stuff into a JSON RPC format, which looks like this, right? This is a JSON RPC format, and we use is 2.0. We have a method, which is the ETH get block number. We have some parameters, which in the block number call is an empty array, and we have an ID, which is basically a nonce. We got to provide nonces, right? Otherwise, things can get crosshaired with EVMs. So we set all this up. We do some SERDE and conversions. So we have this JSON RPC string here, and now we're doing a curl call. So now you ask, where does curl come from? Curl is another adapter, another WebAssembly component. And it doesn't do much, but it's really important. This is how we get around the socket restrictions in WebAssembly. So WASI, or WASM IT, which compiles to WASI, is really like a very secure, very sandboxed, and fundamentally quite deterministic execution environment. As I said, we need a way to use a socket, and we don't have a socket. Through that sandbox and access host resources, which need to be permissioned by the host, by the way. So it's not a one-way street. You can't just start using host resources without being permissioned by the host. And this actually is going to come into the billing model, which we don't have quite ready yet, but there is a billing model around all that. And if we have time, we'll get into it. And so basically, the way this works is use FFI to link the binary from the host, from the peer, and make it available for call. And the output is a mounted binary result. And that basically is just a data structure or an interface, whichever you want, or depending where you're coming from, that includes fields such as standard out, standard error code, and some other stuff that you would usually get with the call from a binary. And now we're using, so this is the marine macro. The marine macro does a few things. One of it checks types, because WebAssembly has a very limited set of types. And which is actually a good point right here to do a detour. If you haven't used Rust and you know it's very difficult, it's very powerful, blah, 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 it is. It's awesome. But it's also difficult to learn, right? Yes, it is. But WebAssembly has very limited types, and everything is passed by value. So all the very cool stuff about Rust, all the type safety, a lot of the compiler checking that makes Rust so safe actually doesn't even come into the picture. There are no lifetimes. There are no generics. There are no major traits that can be passed, types that can be passed. It's a very limited set of fundamental core types: ints, floats, boolean, strings, bytes. That's pretty much it. There we have we created one additional type, which is called a record, but it's composed of other ones, and you can customize that type if you want to. Look at documentation, reach out, we'll show you how, if you need it. And so we basically wrap this this binary call that sort of from the WebAssembly in Marine calls into the binary of the host, gets result backs, wraps it into this mounted binary result structure. And we now wrap this and expose this so it's callable from the REPL or any other module with this call. And that makes this curl request function, this is now public. This is publicly callable. Okay. Now, if we go back to our multi-provider one where we said, hey, where did I detour? Okay, here was the curl call, right? This is where it's happening. This is where we query the blockchain gateway, right? This is where all the request action is happening. And I said you can't import anything, right? But you can link it runtime. So one part of that linking in runtime is we link through a WebAssembly FFI, which we call it an import module. It's not really an import, it's a link, but which is clear. And we import the publicly accessible function of that curl WebAssembly module, which literally was just a wrapper around the binary call, which we call curl request. And it takes an array of strings, just like you would do with any CLI call, standard process, whatever, right? And so now we get back our response. And now we do a whole bunch of error processing, yada, yada, yada. But at the end, we return something called EVM result. And EVM result is, again, it's a struct that, where is it here? That basically gives the provider name. So the gateway we called could be Morales, could be Infura, could be Alchemy, whatever you're using, and the standard out and the standard error. And the standard error, so now what's the standard error? What, as I said, like that mounted binary result that has standard error, standard out, and some other information, and we just basically work through it. Standard out contains the hex string representing the block number at the EVM. So what we're doing is, if we don't have an error in our response, we basically try and convert that raw response, which is just basically what we got back from our curl call, and turn that hex string into U64, being optimistic here, block growth, of course. And then again, if this is all working without errors, we don't have any problem, you basically get something back where you have a provider name, right, which was whatever it said it was, and basically it gives you back the block height. But we now wrap the block height for reasons, just for management reasons, into a JSON object, which we stringify. And so the result, if everything goes well, is this EVM result. And if we go EVM result dot standard out, you should end up with a JSON string that says block height, block dash height, and the actual U64. That's all there's to it. Okay, so in order to query a gateway provider, we need some socket capability. WebAssembly doesn't have socket capability. We have a way with Marine to access the host, the peer host, needing the service, this binary, curl in this case, to give us socket capabilities. We use this capability, we do some calling, we do some response processing like you would with anything else, and we end up with a result, which is a data structure comprised of the provider name, the gateway provider, the standard out, and the error. That's it. So if we compile all this, while we're compiling, I told you we have this script where we build now our WebAssembly modules. Ignore all the other modules. There's some more modules, and there's actually an entire repo for this project. It's got a pretty extensive README, and I'll share the URL in a minute. But yeah, have a look, because there's other things you can do in terms of using IPFS for providing function parameters to functions and all that good stuff. But here we go and compile this, and basically what we're doing is we make sure everything's updated from the Rust side. And this Marine build release is how we build the WebAssembly module. And then we just copy the resulting WebAssembly file from the depth of the compilation tree into this artifacts directory, so it's easy for us to access for deployment and other things. Plus, you can do cargo clean. Why do you need release there? Word of warning: if you use if you build WebAssembly modules in debug, you get many gigabytes of output. There is enormous debugging output, and whereas if you do it with release, you're like in the kilobytes. So it's just a fair warning. For the most part, you want to do release. And so we run the script, and here everything gets compiled and basically put into this artifacts module. So now I talked a little bit about the REPL, right? So we need to, when I said we build these services, we need to give some information about these WebAssembly modules, how they're used, and what limits they get. And also we want to introduce a namespace for them. So what we're doing here is we're building a configuration which we can use in the REPL. This is only for local use, and we basically specify what the WebAssembly module's name is, how much memory we want to give it. This is extremely generous, by the way. I don't know what I was thinking. And whether we want logging enabled. And what we can do now is we can use the Marine CLI tool, and we go into, what was it? And now we're in the REPL, where we can now interact with the WebAssembly modules we just created. And if we type interface, it shows us all the exported data type, which we created. Those were those structs, those interfaces we had in our Rust code. And those are the functions we exported. So this was the function we wanted to do. So hang on. So what we're going to do is, okay, this is suboptimal here. I'm using a link to do a call to get a block number, because it doesn't require an API key. So I don't have to give you my API key, which means I don't have to reset up everything out there. And so basically call this module. This is the namespace of the module. That function we just briefly reviewed, with those parameters, right? Remember, the parameters of function signature was the name and the URL, which was the data struct for provider info, I think it was called. And we do this by basically giving it curly bracket data structure. All right, if we run it, all right, we get, remember the formatted JSON string we wanted in this EVM result? Well, here it is. This is what we wanted. And so we now, our module works. Now, we also had a quorum service, which I haven't gone through. Let's do this first before we go here. Quorum service. So basically, what we do in a quorum service is we calculate the mode and the frequencies and the mode for a particular number of data items, coming from point estimate coming from an array of those EVM results. Remember, EVM results were the structures we got from each one of those calls to the gateway providers. And now we join them into an array. We pass this array, and this is where we calculate the frequencies and all this good stuff. And then somewhere down there, we also have a function that basically takes a nominator, a denominator, and the threshold. So if we have the denominator is the mode of the returns, so the largest number of like values that came from those 9 responses. The denominator is n, 9, because we had 9 times, and the threshold is whatever you want it to be. So if it's 2/3, it would be 0.066. And then we just basically do a quick calculation, and we do this as a service function, as a service fundamentally, not directly in Aqua, but as a deployed service. And we'll check whether our response is a quorum. And here we can just test the quorum again in the REPL. And I don't know, we have 2 values out of 3 that are the same, and we want a 0.8 threshold, and of course it's false, right? We go to 0.66, and okay, our calculations work. So this is how you can test things interactively locally on your values, on your modules. Sorry. Okay. So now we have these services, and now we want to deploy them. And now I really got to start to hurry up. So the way you deploy them is you use the Aqua CLI tool, for example. There are different ways to doing this, but one is the Aqua CLI tool. And what we do is we basically, hang on. Now I'm going through the README as quickly as I can. Here, we write something like this: Aqua remote deploy service. That's the command. We give it an access point into the network, and this is basically a typical lib2 peer-to-peer multi-address. We give it a config path to our deployment instructions. I'll go in a minute. The service we want to deploy is called the multi-provider query, which, remember, was 2 modules. You need a secret key, which you can create also with Aqua. That secret key basically is required if you want to delete the service and or if you want to authenticate access to the service. And then when you upload it, you end up with a blueprint and a service ID. So the blueprint, and we do this for three different peers, right? And if you look, the blueprint is always the same. Basically, the blueprint is the result of hashing the WebAssembly modules plus some other stuff, and it's always the same. However, we need a distinguishable access address to the service, and for this we create a unique service ID, which is basically UUID4 that maps to the blueprint for the retrieval of the modules. So now you can service. So now you have a service address comprised of service ID and peer ID that allows you unique invocation of services anywhere in the peer-to-peer network, as long as you have something that matches that service. Okay, so once you deploy this, you can use it, and you use this now with Aqua. And I wrote a bunch of different ways of doing it. So one of the things is if we want to do it, get blockhead with quorum. So we have our provider infrastructure again, as we've seen here from before, data, right? And we have the EVM results like we did before. And now we're going to add one more data structure, which is our function address, which is literally the peer ID, as I mentioned before, and the service ID. So if you now want to run this, you don't really have to do much. You declare a bunch of streaming variables, basically values you can write into from stream. And then you basically say, hey, look, now the addresses are those different peers, right? Are those function addresses, which was an array. And we say, hey, look, on each one of those peers, in parallel, execute this get block number function, which we initiate for each one of those, on each one of those peers, by basically taking this multi-provider service, which is the namespace here, with the block number relative to the service ID, and then we just pass on whatever values we have. And then so we're now in parallel on different peers simultaneously, right? In parallel, sorry. And then on each one of those peers, run for each provider address, which were 3, the query get block number for each one of those providers. So we're orchestrating the execution. First, we compose the services, and then we orchestrate the execution in parallel 3 times per parallel arm, each peer, right? And then we join all the results back, and then we actually use this simple quorum point estimate like we showed before, and return a result. And now let me just find in here where we run it. Okay, 5 minutes. This is getting black eye quorum. Okay, let's just see. Okay, we run this now. I have a slightly different parameter file. So what we were doing is, well, actually, let me run it first. The parameter files in the repo are without the API keys, but you need API keys to run it. So except for link, and hang on. Help.
Just curious here, Bernhard. Do you have to specify the API key in a file, or can you just type it right into the command line?
Well, you could. Let me.
I mean, obviously, you wouldn't right now.
Right,
but I mean, in general.
So okay. So I'll get to this like in 1 second. So we basically use the CLI to run it. You can actually run it from a JSON, not JSON, from a JavaScript or TypeScript client as well. But this is sort of a one-shot deal, and it gives you a little bit of what's happening and how these streams are built up and who's responding how. So basically, what we got here is we got 8 out of 9 responses, and this is our mode. This is this block number. So is 8 out of 9 is this number. And we said, hey, we want a 2/3 threshold, 0.66. And so not only do we have this point estimate, but we actually have, yes, it is a quorum acceptable value. Okay. Now, so hang on, let me go back to that one more time. So the way we called it is, so Aqua run is the run command, right? That basically sets up the one-shot client peer. We give it a relay address to connect to, and then we basically say, hey, use Aqua from this Aqua. Use the Aqua file from this directory. We don't even have to specify which one. It'll find it on its own, because what it actually does is it compiles it into the intermediate representation without you having to do anything, and then execute this get block height function with those 3 arguments plus the threshold. And now if you go back, is you can write in the JSON strings if you want to in each one, but it makes it for really, really ugly function signature. So what we instead did is we say, hey, we import all those parameters, those arguments from this file in this path, and it was in parameters quorum, blah, blah, blah. So now what you can do is basically, this is how you can structure it, right? Where you basically say, hang on, here. So this was argument 1, right? So this is our provider information, like we discussed. And this is the URL. And then you add your API key there. You could type it in, but you don't have to. You can actually obfuscate it a little bit. It's on your client, so it doesn't really matter. But it's either way. You can type it in, or you can just put it in your file and do it. So for me, of course, it's easier. It's much cleaner to put it into this structure for these long ones. Plus, typing in JSON strings as arguments is, in my opinion, it's a PETA. But yes, you can type it in if you want to. Long way to answer this question. So again, so basically what we did is what we just executed was this, right? And Aqua allows you to totally abstract about everything that has to do with discovery, content routing, connecting to peers, moving between peers, piping data. It abstracts all over it. It's not magic. There's no magic there. It just abstracts very cleanly all over it. And really at the core there is, so every time you do this on this peer in parallel, you literally, part of this particle now executes on each one of those peers in simultaneously, and then at the end gets joined. So we have eventual consistency in our data. And if you, this is like, I mean, this is truly like, this is like really, really cool, because in fundamentally 1, 2, 3 lines, 4 lines, in 4 lines, you can actually orchestrate a arbitrary business logic workflow over an entire peer-to-peer network, entirely infrastructureless, because you could run, like we just did, this whole thing from a client, but you actually could mount your Aqua script similar to a cron tab on any one of those peers in the peer-to-peer network, and then have it periodically executed if that's what you wanted, and written, for example, into an IPFS file, and or onto IPFS, and put the CID somewhere. And so fundamentally, you could go totally infrastructureless off-chain if you want to, and not only be serverless, but also be clientless. And now I'm really running out of time, and I apologize. So if you have any questions on this, reach out on Discord, or Telegram, or any one of those areas. And let me just get to where you all probably have been waiting for the last 60 minutes to get to. We're supporting all the tracks of this hackathon with $5,000 each, $3,000 and $2,000. In metaverse and gaming, for example, let me make it a little bit bigger. Things that are really cool you can do with Fluence is to enable dynamic NFTs, do live score updates, all these kind of things, like you just seen with a quorum/consensus. So it's sort of a first-person oracle if you want to, and it's actually really, really cool if you want to do this. We have the tooling track. Kind of mostly interested in improving Web3 tooling, but if you want to improve Fluence tooling, go for it. I'm all up for it. Cloning Web 2, obviously everything you've seen, these services are fundamentally function-less services, right? So cloning an Amazon Lambda, for example, or parts of it, let's put it this way, and would certainly be a very, very cool and much appreciated hackathon task if somebody wants to step up. And tracking doing good. So Fluence, where I think we can help most in doing good is by making DAOs better. And one of the things you can do is you can you can add Aqua, you can encode, add execution and workflows to your DAO proposal that then can be automatically executed, totally verifiable when a proposal gets accepted. So basically, you have a DAO proposal that needs to execute something. You write that something in as a mix of Aqua and services. You attach all this stuff as a package to your proposal, and then when it gets approved, hopefully, whatever code you wrote, whatever service you have, get executed. You can set them up, you can tear them down, you can scaffold the whole stuff. And that's actually really, really cool to really, really bring code as law literally to the execution flow of DAOs. And then, of course, we have another 5 prizes for the best use of Fluence with Morales and our Filecoin, or all of the above. And that's it. I'm sorry I went over time.
Oh no, that was wonderful, Bernhard. Thank you so much for taking as much time as you did with us, because I'm with you. I'm especially near the end of the presentation, I'm seeing multiple communicating with multiple relays simultaneously, and scheduled scheduled jobs and things like that, and my mind is just blowing, and I totally missed that we'd gone an hour myself. So absolutely no problem whatsoever.
And so, and I know it's a lot to digest. It's Fluence is extremely powerful, and like with most powerful systems, particularly, I think it's very usable, but it's not super, abstracted. We're still like a lot of improvements. So contact us. You can schedule one-on-ones, go to Discord, go to Telegram. We want you to succeed. This isn't like high school or university where we want to filter out, we want you to succeed, and we want to do everything other than write it for you for you to succeed. That's Absolutely. What we're here for. That's what we want. And utilize the resources. And just a word of caution, I've done hackathons myself. Don't leave it till the last weekend. It's too complicated. Don't leave it. Like, ask your questions before. At least ask the questions before. Other than that,
of question and answer, we have a question and answer coming up in just about 15 minutes in Gather.town. Take a look at the link in the description below the video. We're going to be there for at least an hour. after this event. And Bernhard, you're more than welcome to join us there as well, if you have the time. And yeah, that's a great advice. Do not wait. Start your projects early and start your questions early, because we want you to all be successful. Every single person who's part of this hackathon is part of the first 1 million developers in Web3. The first 1 million developers building the metaverse. You're part of that right now if you're part of this hackathon. And don't take that for granted, because this is an opportunity to really build the future here. Thank you so much, Bernhard, and good luck to everybody who's participating in the hackathon.
All right. Bye-bye.